3, 2, 1, 0. We have commit and we have liftoff at 2:13. The Saturn V building up to 7.6 million pounds of thrust, and it has cleared the tower.
Well, actually, I am the first one up, and we do have a great panel. And what we're going to do this evening is each one will present for about 20 minutes. Then we'll have 10 minutes for questions and answers after that. And if there's any remaining time at the end, we'll do that. But if during the time we all have mics up here, you want to ask questions, and we can respond to them, we'll do that. So right now, Ben Donahue will give us some discussion on space transportation, a little bit of focus on the moon, and then Nikki Werkheiser is going to talk about in-space manufacturing. That's a pretty exciting area, and she's in the middle of it. And then Dr. Percy will follow with a discussion about Mars. So we're covering a lot. We're looking ahead, and thank you for coming out. This is a special time for me to be here in the celebration of the Apollo 11 landing. It looks like most of you were able to watch that real time, and I did too, and it was formative. My career is pretty much based on the excitement of manned spaceflight and landing on the moon. I mean, I think of the guts that the U.S. had to launch somebody to the moon with cameras. Success or fail, we did that. And still, when I see these slow motion versions of the Saturn V lifting up USA, wow, that is pretty special. And it happened here. So I am really honored, and thank you for inviting me to be able to be on this panel. I don't consider myself a futurist, but I like to dabble in things that I think can happen, and they haven't, so I guess they're part of the future. I'm going to focus on EVA, and I call it EVA Plus because there's a few other things that are mixed into this. And EVA deals with extravehicular activity. Depending upon your background, that typically means spacewalking. I'm going to show you a little bit different side of that as well. Now, there have been many spacesuits. These are most of them. And they come soft, they come hard. They come Russian, Soviet, they come US. So there are lots of ways to do it, but most of them are anthropomorphic. And who doesn't look good in a spacesuit? I mean, that's just what you want to look like. That's the kind of epitome of an astronaut. Well, there are other ways of doing it, and I want to distinguish the EVA part from something else that people generally call spacesuits. They're not going outdoors. They're the suits that you need if you lose pressure in your launch vehicle or your capsule. So those are there on the left. You'll see it's called the ACES suit. It's the one that we see for most of the astronauts that flew in the shuttle, the orange one. And then now Boeing and Elon Musk have come up with their own concepts. These are basically pressure suits in case, like I said, you lose the cabin atmosphere inside your capsule. The others on the right-hand side are examples of the current suit. Oops, let me go back. Right here, which is the EMU. This is what they're planning for on the moon. And then this is a different approach. Basically, it's a leotard type suit. It's not new. It was done in the 60s, but it's come back, and it uses compression rather than atmospheric pressure. So these are some examples of suits that have been proposed for going outside. Now, I also want to explain why we need to be looking at a different concept for weightless operations. When we went to the moon, we were able to walk with our legs. That's natural. These are gravity muscles right here. But when we're in the weightless environment, we have to use these small muscles that are in our arms. So now we're using muscles that weren't intended to be legs for translation and mobility. Suits weigh around 300 pounds. You add your mass to that, and you've got to manage that. Being able to get out to the work site, set up the work site, do your job, and be able to get back, all with these little forearm muscles. So that's something that is a little bit different. The legs are not really used, so it's not a spacewalk per se. The legs are a load path for doing action on orbit. Now, one of the things that I'm working on is called a single-person spacecraft. It's not new either. Von Braun had this. But it's a very small capsule that would allow you to get out and do work. It has its own propulsion, and it has robotic arms in order to do that. Now, another distinguishing feature is that when you're on a planet, either Moon or Mars, suits make sense. But when you're in the weightless environment, like I mentioned, you're having to move around, and a propulsion system allows you to get where you can't go in a spacesuit. And some of the things that are on space station, like the solar arrays and the radiators, are in harm's way. And you have to be able to get out there sometimes because it might take a micrometeoroid hit or a debris impact, and you have to repair it. This allows you to do that. The other important advantage is that suits are designed by glove pressure. You want to get the pressure as low as possible so I can actually manipulate the 11 layers that are in the glove. So they bring it down to about 1/3 of an atmosphere. And in order to breathe, you need pure oxygen. So if you see astronauts getting in spacesuits and going out, that doesn't happen. It's 12.5 to 14 hours pre-breathing pure oxygen before you can actually go out in the current suit. Now, the capsule that you see there, the single-person spacecraft, is at the same cabin atmosphere and gas composition as the host. So you can get in it and go, no problem. So that is a big advantage for future spaceflight, and one of the things that is built into that. That's the reason why it doesn't have, in some concepts you'll see, these gloves and arms that are extended from that. You're back into the same pressure. So this allows you 14.7, nitrogen, oxygen, and you can go do your EVA, fly out there and fly back. And we've sized this thing so anybody can use it. All of you could get in it. And we've tested that to see if that would work. It's not like a suit. A suit has to fit properly. You don't want your arms going away from you when it's inflated. So it gives you a lot of advantages for future spaceflight. We built a prototype of a ground or surface suit, and it's called the Command Control Pressure Suit. And there's a reason for that. Because right now, like I mentioned, the pure oxygen environment inside the suit, they do not like to have any ignition source, no sparks. So they tend to keep all of the stuff outside. Put it on the chest, little LCD display for things. But you need to have informed astronauts. They can't train for everything, and a lot of times you have to deal with contingencies. So you've got to be able to provide an information system for the crew. And this allows that. You package some instrumentation inside, and then you can delay. Here's some concept sketches, and the first thing you see is that it really doesn't look like a helmet. And it's not a helmet. It's more like a cockpit. And the current suit, you take off the helmet, you disconnect the gloves, and you have a body seal closure that's here. And all of those parts have to come together. This one basically just has a rear hatch that closes. You size it for yourself, you get in and you get out. And it has faceted panels, largely because if you want to make those panes thicker, you can do that and you don't have a distorted view. If you have a bubble type canopy and you make it thicker, you're into a lens and you'll have a distorted view. So this gives you the capability to have thick glass and be able to have clear view. And in order to take it a little bit further, we built that mock-up. Another thing that I'd like to point out is that here's an example of the displays. We redesigned the boot and the sole on the bottom so that it wouldn't capture any rocks and lodge them in there. But can you imagine the advertising potential of having something written on a boot and how long it would be there? I'm surprised somebody hasn't done that with a rover. You know, as it moves across, it's, you know, actually displaying some kind of logo. And then another aspect of this is, here's the current suit with the helmet, the gloves, and then the lower torso. And now the way that this command control pressure suit works is that, you know, you get in, and on the moon, the dust isn't dust. It's shards of basalt. You know, it's abrasive, it's toxic, and what happened on Apollo is when they got out, some of that actually got back into the suit when they got into the next time. And when you pressurize it, it goes back out. So there were times when it was very hard to get the wrist locks going on the suits. It's a big issue. Now, if you minimize the break points in the suit, then you can control how you clean the suit before you get in it. And that's why on this image you can see there's just one part. The other thing is the center of gravity. Rather than having a backpack, we're trying to bring the center of gravity a little bit forward, and that helps in terms of mobility. Now, we built a full-scale prototype, like I said, and you know, Harrison Schmitt was good enough to get in and gave us an evaluation. Now, that was important because he was on the moon doing geologic work. He went out several EVAs, and he had a good appreciation for what it is like to be in a suit. And he liked this suit. He liked the visibility that's provided. Currently, suits do not have helmets like motorcycles. If you turn in the suit, you're looking at the side of the helmet. You know, so this allows you some visibility out the side. We also tested it in 16G on the KC-135 that does the parabolas, and the purpose here was to see how you could get in and out, because this is before they did really any testing on the US side for rear entry suits. Now they're being a little more popular and being able to do that, but it was an important aspect of affirming that our design was working. Now, the command control part of this is important. You can see the vehicle there, and going back to the Apollo, the walls of the lunar module were very thin. Astronauts were cautioned not to kick them because they could put their boot through it. It was a very low pressure, and they didn't need to be that way, and they were very concerned about mass. And it's not fully appreciated either that they flew those things in their suits standing up. So, you know, the thought is, why do I need that enclosure? Why can't I just fly out in the breeze? So this suit was designed, you know, to stand on a porch and fly it. And, you know, like you would the manned maneuvering unit. That allows you to lighten up the whole vehicle. You get rid of that cabin, and you allow the crew just to fly it that way. So it's a little bit different concept, but this is a possibility, and I think an exciting possibility to be able to fly. You could almost fly into orbit with this thing, and what a ride that would be. Another application of this, we tried to make it modular, and especially in the backpack, because when you go to Mars, you're now at 3/8 gravity rather than 1/6 like you are on the moon. The moon's pretty forgiving. You can have a pretty heavy suit and still get around. But on Mars, you have to watch that. So, you know, we have a smaller backpack capability, and we can use a lot of the same parts of the suit, and hopefully it'd still work there. There are other technical issues with doing EVA on Mars. I want to change to the single-person spacecraft now, and point out that the neutral body posture, the form that we take in space when we don't have any gravity on us, is basically like this. Our muscles in their neutral condition. We wrapped the design around that right here. So it's a very small vehicle. But unlike what you saw in 2001: A Space Odyssey, where you're sitting down, you know, and that movie was done before we actually discovered this stuff in Skylab. But this takes a little bit different approach. I wouldn't say you're standing up, but it responds to our natural posture in the weightless environment. This is a view of it in low Earth orbit, and what we've done so far to take this further than anybody else is build a full-scale mock-up and a flight simulator. We have the ability now to get in there and fly around the International Space Station. And we've put in all the control logic and rules for our propulsion system. And actually, I've had some astronauts in there that have flown the shuttle, and they say we're dead on for our control for this. Another interesting aspect of going out EVA, in suits, you never turn any nuts and bolts with your gloves. That's forbidden. So an astronaut, to a large extent, is a tool positioner. They go out, they get there, they put a tool in their pressurized glove and put the tool head on the job. So we're saying, is that the right solution? Maybe you need a little bit different way of approaching it. So in this, we've looked at the medical robots, and we're working with SRI out in the Silicon Valley. They're the ones that developed this and then licensed it. Now they're developing something called Taurus, which is a bomb defusal robot. And we are using that. And it's a little bit different than the normal anthropomorphic, two hands on the job. We have one arm and a very smart end effector on it. So that's what we're doing. And this end effector, you can see there, it's going through the window of a car and it's unzipping an athletic bag. So it's pretty capable. And those are the type of skills that we're going to need when we're, doing repair and maintenance in space. This is some of the neutral buoyancy work. We have a small 24-inch hole in the bottom. Didn't know whether or not we could get everybody in and out of that, so we needed that. This is not at Houston. It's not in Maryland. It's right out here at the Space and Rocket Center. And they did a great job. We had a full range of test subjects, and we were able to confirm a lot of things, not only the ingress and egress, but foot restraints and also the controls. This is very applicable to what NASA's looking at in its Lunar Gateway, that all we need is a little conical interface to berth with. Otherwise, if you're in spacesuits, you need an airlock, you need all kinds of support. This would save thousands of kilograms if you were to adopt this approach. And you have direct access to space. We've tested a demo flight structure. We built this and done a pressure test at 1.5 times its maximum operating pressure, and also done a leak test, and we're well better than what Space Station has. Also, you can see right here the SPS is out servicing a solar array at our version of the Gateway, and the Gateway does not have an airlock, and that'll save you a whole trip out and a lot of mass. Another concept is a lunar lander. This was done a long time ago, and I was talking with propulsion engineers. We've got some here. They usually like centerline thrust, because if something goes out, you don't have that off-axis torque that you have to control. But what that gives you is a solution like this, where you've got the payload on top of a lander, a payload on top of a lander. And then you got to figure out how to get it off. And in the studies I've done, you usually bring along a lot of extra equipment to try to get it off. So you're kind of creating another problem. This concept says, let's fly horizontal. Let's put our payload right in the middle, the CG, like most every other transport vehicle. The airplanes or ships or things like that. But let's make it like a 4-engine aircraft. So if one of those engines goes down, I throttle up the other, and I oversize my RCS, I'll be able to land. And then I've got modular payloads that I can use on it. So this is a horizontal lander concept, and it's very good for offloading. Propulsion engineers are going to have to work a little overtime, but I think they can do it. And these are some of the early design concepts here of showing that. And this is the crew module, and you can see a view of it, and then the lander. And this plays into a larger scheme. I don't like to design just single elements. They are part of an architecture, a broader way of looking at it. So for this lunar base concept, the idea is don't change the surface. That's very hard to move around. Again, it's adding equipment. We don't think much about it now. You do all of your ground improvement. Here, you leave it, you put down these footings, you build up, and you establish a plane that is above it. And then you hang things from that plane. So that's your level. And then this also has an enclosure for radiation protection. So this is a way of using the elements that you just saw in order to build up a lunar base. Another concept is for a rover, a small pressurized rover that doesn't come down on a lander. It has a stage to decelerate, and then it has a terminal stage for the final landing. And the reason this was acceptable is that when you look at the acceleration loads for landing the Apollo landers, they're pretty low. They're within the range of most suspension systems. So this took that and said, okay, I'm going to design it and be able to have a rover that lands on its own, no stage per se, and then drive it away. And that, again, is an efficiency matter. Then this is a Mars lander, and it couples into a much larger overall architecture. Elements that you see on the ground have already been delivered, and this is how the crew gets up and down. Landing on Mars is more difficult because of the atmosphere and being able to get down through that. I was asked to look at some of these more far-reaching concepts of generational starships and things. And this is way out of my comfort zone. But in this, the habitat portion of that spacecraft is right there, and that holds 500 people. Something called a Bussard ramjet. It goes around, it collects up hydrogen, and you're accelerating out into the star. And then another one is a generational one where these three ships here, they house up to, I think it's, 6,400 people in this one. But that first generation is not going to make it. Their babies might, or their babies might, but that first generation won't. So that's the end of my presentation. It shows some EVA, it shows some other things, and open up for questions right now. Yes?
Question about spacesuit design. In the process of doing that, and I realize you were concentrating on these single-person spacecraft, but do you consider one person in the sense of it only takes one person to put it on, or do you always have to have a second crew member there to assist the subject that's going EVA in getting the suit on? And I was thinking about in contingency situations, emergencies or stuff, where you might not have another person, and the person may need to get a suit on. Is that a consideration?
You're talking about the current EVA suit?
Or any future suits, is that any part of the consideration?
Usually the requirement is that you should be able to put it on yourself. Now, when you look at the Apollo suits, they had a big old zipper in the back. And that's kind of hard to do. Jack probably knows more about that. But with the current suit, you basically can do that. You get into the lower torso, you bring it up, you lock it, then you get your gloves on, you put your helmet on. You can't. But usually there's always somebody there helping you do that. And then you need to check out your suit for leaks and comm and other things before you go EVA.
And what if you have one of these deals with a back hatch on it? I guess if it's hinged, it'll line up, but if you've got two parts, that could be problematic.
Well, that's right. And anything that you think has a hinge, the hinge is only a way of getting it and positioning it. You rely on the dogs that are around the outside to actually latch it down and seal pressure. That's just an alignment device. So you won't rely on that like a door, typically for using the hinges.
But the hinge would align it and hopefully eliminate any need for another crew member to help with any alignment.
Right. On the suit that I had designed, there's a little lever on the side that allows you to lock that down or unlock it. And also on that suit, there is a provision on the side of the portable life support system to do buddy breathing. So there's a little slack in a hose. If your backpack went down, you plug it into the next one and you walk back together. So there's a safety measure built into that. Yeah.
Is that there in the Apollo suits?
Yes, actually, they could do that with that when we go back to the moon, we're going to find backpacks because they threw them out. They didn't need them anymore. Yeah, they plugged into their suit using the umbilicals that were there in the cabin. So, yeah.
Historically, ISP is almost everything in propulsion performance. Surely it's still, is it still relevant in interstellar?
For interstellar space, I don't know if I'm the right guy to answer that. I'll have to defer to maybe Tom or Ben. I did some research to come up with a design, and I relied on others being the expert and did the configuration. I don't know how you would collect hydrogen, with these big magnetic cones, kind of going through interstellar space. But apparently Dr. Broussard seems to think he can do that, and it's okay. It's nice to have visionaries like that. Yeah.
Arms seem kind of nice to have. Have you gotten any feedback from users on that? On the manipulators instead of actually having arms out there?
Well, NASA is not monolithic. There are people that like this, including crew, and then there's a bunch of them that don't want to change their ways, and they think being in a spacesuit is just the right answer, and we've been doing that a long time, and it's worked pretty well. So, and then there's always people whose job depend upon supplying that, and spacesuits are pretty resource intensive. You always go buddy. You have to have spares, and then also on orbit, because crews are changing out. You're not bringing up spacesuits each time. You have to have this inventory of parts. And when you consider 5th percentile female, which is less than 5 feet, to about 6'3" male, you've got to have a fair number of parts in order to fit them. And that suit does have to fit well. I mean, you've got to be able to, get your hand in the glove and work it. And then beyond just fitting, each one of us has our own idiosyncrasies and what we think is a good fit. So, I doubt any two of us could fit into the same suit. It needs to be tailored that closely. And then there are other things. You have to provision the outside of your spacecraft with handrails. And you go from handrail to handrail tethering yourself. You have to, right now on space station, because it can't get you, you wear something called a safer. It's a mini backpack, but it's like a parachute. It's only intended for emergencies to get you back if your tether breaks and you're free, because that space station is not going to chase you. The shuttle could go after you, but they can't do that. So they have that. So those are a few of the parts that are required. The airlock that they use on space station is a 2-chamber thing. They have a larger one where they don and doff the suit and store parts and things like that. And they have a much smaller one, which makes sense because they pump down that. And they try to reclaim as much breathing air as possible. With the single-person spacecraft, if we are the same as undocking a Soyuz capsule, we're 5 times better than any EVA after pumping, because you just can't get it all out. And that's after 30 minutes. So, that's a long answer to a short question. But, I think part of it's getting the message out. My feeling is you're going to see a single-person spacecraft. I'd love to see USA on it. It's coming.
Well, I guess I don't see single-person spacecraft as separate from having 2 arms where you can just reach out from the front, through the front of it to do something, if you need to manipulate something. You can still have everything else with a single person, but have a way you can reach out.
But once you do that, you're back into a spacesuit. You have to pre-breathe because you want the pressure low, and the crew fit. I mean, not everybody's going to be able to fit into those gloves. Our reach is different. Our hands are different size. And, where we do that and where our eyes are, there's a lot of anthropometrics that goes into making it work. And it doesn't make any sense to have these inflated gloves out there and you can't reach to get them. So, the benefit of a single-person spacecraft is flying at this pressure, these gases, and being able to get out and do your work rather than go through the pre-breathe. And the pre-breathe is so, just like for those who, may have done scuba, is to purge the nitrogen in our system so you don't get the bends. And, they're going to continue to have that protocol. because they don't want a bent astronaut. Yeah.
So does the single-purpose spacecraft use an airlock, or do you not?
We don't need an airlock. That's one of the advantages. You need a little docking cone, and then you can come in, but now we get drones that can fly themselves home, and that's part of the feature of this. It can be teleoperated, or you can fly it. You have a pilot. But it comes back, and the reason for the cone is just to go down to the standard interface that is on spacecraft now and get it down to close to that 24-inch diameter opening. And it would be, you can dock, or berthing in the parlance of NASA is using an arm and having a very controlled interface to whatever you're berthing with. And we're thinking we can use our arms to berth ourselves. In fact, we're thinking we can use our arms to work on ourselves, even if you're not in it. So that's part of how we're packaging our components, is that we'd be able to open those panels up and reach inside and do self-surgery, if you will. Yes?
Yeah, the vehicle that you had on there, the horizontal vehicle, looked like a rover that you had your payloads on.
Yeah.
You said that wouldn't need any braking mechanism coming down upon the lunar surface, is that what I understood?
No. There were two different ones. The little rovers, I didn't show the decelerators, the solid propellant decelerator stage that got you down where you could use the final propulsion system. The horizontal lander, no, it has full propulsion on either side. In fact, it was designed modularly, so I'd be able to take that off, and it was done a long time ago, but it was looking at the in situ resource utilization, being able to, use potentially the water that we find on the moon and turn that into hydrogen and oxygen. That'd be the propellant, and you'd tank up. But the idea is that that's a modular thing. Two engines running half power each when you're going down. So if you lose one, you throttle up, to full power on the other one. And the reaction control system was oversized to compensate for, the control. Yes?
Is it possible that Martian dust will be an even greater difficulty than lunar?
Good point. He talked about Martian dust. As I understand it, it's a lot like talc. It's very fine, and we've seen, global dust storms on Mars. And it potentially could be. And even though it has an atmosphere, that may tend to round off a lot of, let's say, the particulates. On the moon, it's just the impact that has created what we call dust, the regolith that is there. And that's why it's so abrasive and toxic. You can imagine what it'd be like to breathe lunar dust. And we don't know what it'd be like with Mars dust. But both have been looked at, and I wouldn't say they're showstoppers, but they're a major concern. And because it's unavoidable. Every crew member that goes to the moon or goes to Mars is going to need a spacesuit. So they're going out. And if they go back in through an airlock, they're bringing that stuff with them. So we have to come up with some ways to control dust contamination. Okay. Well, thank you so much. We will go to our next panelist. Our next panelist is Ben Donahue. Is this on? Okay, now. Let me introduce Ben. I've worked with Ben at Boeing, and good man, has come a long ways, and enjoy working with him. Let me tell you a little bit about his background. Mr. Donahue is Boeing's Space Launch System Principal Investigator for Internal Studies. He has served as Boeing's lead for upper stage evolution studies, payload and exploration mission identification and optimization, concept design for exploration payloads, propulsion system analysis, launch vehicle, and in-space stage simulation. He was Boeing's lead configurator for the NASA Altair Lunar Lander study, responsible for systems engineering and propulsion systems analysis. Ben was the lead engineer for the Lunar and Mars in-space transfer stage and lander concepts on a NASA transportation study. For this, he was responsible for propulsion, configuration, and architectural tasks. Ben has a Bachelor of Science in Mechanical Engineering from the University of Alabama. Let's welcome Ben.
Well, thank you. It's great to be here, Brand. Thank you for the invitation. And presently, I do mission design for the Boeing NASA SLS Space Launch System. It's the shuttle replacement, going to fly perhaps in 2020, 2021. But what really facilitated these great lunar missions in the 60s, and I was 10 years old when we had that landing, was a very heavy lift launch vehicle, the Saturn. I once talked to a Russian engineer. He was in the States. He had an interpreter, and I asked him what did he like about the Apollo program, and he said, that Saturn rocket. They were so impressed with the capability. We're going to recreate that capability with the SLS in a couple of years. With Marshall, our NASA customer, we're even now designing, manufacturing, and testing this at the Michoud Assembly Facility in Louisiana. Just like the Apollo system, the Saturn system was built there as well. It, like the Apollo system, will be shipped to the Stennis Space Center in Mississippi. There it will be tested. And so we're kind of following the path of the Apollo. It's Apollo-class launch vehicle called the Space Launch System. So I've got a task, a very enjoyable job of figuring out what missions are best suited for the SLS, how to simulate outer planet missions and lunar missions and Mars missions, not unlike what Brand does or what Tom does. So we kind of do a lot of the same things, which is mission development, concept development. What can you put on a rocket with this capability? So I'm going to start out with a little bit about the rocket, as sort of an advertisement for my company. Then we're going to move on in the few minutes to what are the missions that can be enabled by this. See, the Saturn enabled the lunar missions. Without it, couldn't have landed on the moon. And so the SLS, like the Saturn, is going to be a heavy lift rocket. It's going to enable some great missions that you couldn't do otherwise. Here's 4 launch vehicles, Falcon Heavy, Vulcan from ULA, and 2 versions of the SLS. The SLS is actually a family of rockets. It will grow in capability. And you can see that the gray bar represents payload in metric tons launched to what we call translunar injection. That's the amount of mass you can throw towards the moon. And quite a bit of excess payload capability is provided by the SLS rocket. It'll be the nation's big heavy lift launch vehicle for the next 20 years. And so that's going to be up and online. It's going to enable some really big missions. Missions that require really big pieces, like the Mars missions that Tom studies. These are big pieces, the big lander, the big transfer habitats that have to be in space for upward of 3 years. It's hard to make those small. It's hard to put together many pieces in orbit. It's better to launch them as one piece. So the SLS is going to enable these Mars missions and lunar missions by launching very large single-piece elements. We also look at very high energy missions, going to Pluto, going to Saturn, Neptune. Enceladus is an interesting moon at Saturn. It has a liquid water subterranean ocean, as does Europa. And so the other great advantage of a big rocket like the SLS would be you could launch payloads smaller but much faster. And so there's more than just putting heavy payloads up. The big rockets enable exploration to the outer planets. They can get there in, say, 4 to 6 years versus other approaches. So that's part of designing for missions. Congress has funded 2 separate launch platforms for 2 different versions of the SLS. That's going to help us. The third advantage of the big rocket is very big payload volumes. We've got 8.4 meter diameter fairing standard with a possible growth to 10 meters diameter. Think about 10 meters, Brand, for a size of a payload. And so you can put one-piece monolithic optic telescopes at just one-piece mirror that would be 400 times the fidelity of the Hubble, and it wouldn't have to deploy. A lot of the James Webb Telescope difficulties are due to this folding mirror and all the problems associated with deploying big pieces. If you've got one large launch vehicle, you can launch them as a single-piece element. So aside from selling the SLS, I can say that it's in production at Michoud, well on our way to getting pieces integrated, going to be tested. Extremely large aluminum lithium tanks, interstages. There you can see some of the tanks as they're finished coming out of the Michoud facility. The engines are based from the shuttle program. The shuttle program called them the SSME engines, that renamed the RS-25. We have 16 left over that we're going to be using for the SLS. So it uses heritage components, flight-proven engines. There's an article being barged to Marshall here in Huntsville for a testing. There's a lot of great test equipment at Marshall for testing very large structural test articles, some of which have heritage all the way back to the 60s and the Apollo program. So we're going to be doing similar testing. And a green run is coming up at Stennis to test the core stage. So now let me talk about missions. Part of my job is to come up with and evaluate missions that are suitable, and that's where we get into the exploration idea here. There's a lot of great future exploration that can be done over the next 30 years if you have the tools necessary to get heavy payloads or exciting payloads or small payloads really fast. And I divide them up usually into 4 categories. If you were doing it, you might divide it into other categories. Human spaceflight is obviously a big category. Different places we can go. Science community is very interested in getting to the water giant planets and the moons. Astronomy is important. And then there are DoD missions and other missions that if I had more than 20 minutes, I would discuss those other ones. But exploration is what's going to be enabled by having a big Saturn-class rocket. Now, the shuttle was a big rocket, but a lot of that was not payload. It was actually the weight of the fuselage of the orbiter. So you were launching a lot of weight to orbit, but it couldn't be payload because all that fuselage had to come back. But if you produce an expendable rocket, then all that can be payload, and so that's a great advantage. One of the first missions that the SLS will launch would be a mission that launches the crew on the Orion to the moon. Of course, you know the Orion is NASA's new very large lunar spacecraft, and the SLS and the Orion would launch together and would place the Orion on a trip to the moon, and it would be the spacecraft for doing that. So that's a matched pair. There's an example of a trajectory that would go around the moon, a free return trajectory. Here's an example of the Orion spacecraft with a big upper stage. The SLS is a family of rockets. The first child of that family is the Block 1, has a upper stage taken from the Delta IV rocket made in Decatur, by the way. And then that will grow into the Block 1B that will have a much larger upper stage, 3 times as big, that will be developed here in Huntsville. And so when we launch the Orion, we have an adapter that goes underneath this Orion capsule. And that's at least 10 meters in height, and so there's a good capability to co-manifest, launch secondary payloads with the Orion. And possibly this will be the way that we'll launch the space station in lunar orbit called the Gateway platform. Is a small space station in orbit would be launching an Orion with a separate module. Each launch with the SLS, the SLS has enough payload capability to launch 2 very heavy pieces, the Orion and a habitat module, logistics module, and other things, so we can build the Gateway with the SLS, each time taking crew. Eventually we have several modules, and then we can begin missions to the moon based on a system that's in lunar orbit. And so that's going to free you up to do some missions that don't have to come back to Earth each time. And so Brand mentioned and showed a picture of the Gateway in lunar orbit. You can also fly, has a co-manifested payload, some robotic lunar landers. There's interesting places on the south pole of the moon that have hydrogen in the regolith. You could mine for water. And there's some perpetually shaded craters that never see sun, and there could be water ice right there and there. So you could land there, demonstrate volatile extraction, and make oxygen out of the lunar regolith. And then that oxygen can become rocket propellant, and it becomes something that the crew can use. So part of what you want to do in exploration is launch big pieces, land them on the moon, and then mine for valuable substances like oxygen, and then use that for propellant and other uses. So you begin to live off the land, so to speak, though the moon is a difficult place to live on. But you can begin to think about in situ resource utilization. One of my favorite missions, and Congress has approved this for the SLS, is a mission to Europa, a moon of Jupiter. It has water geysers, subterranean water ocean. And so Congress has funded in the near term, perhaps as early as 2024, the SLS to launch a very large payload that would fly to this moon of Jupiter and then examine that particular moon. It's one of the most interesting moons in the solar system, and that's a mission that's approved. One of the great advantages of the SLS is that it can save 4 years in the trip time. So launching on a typical rocket like an Atlas rocket would require 6.5 years to get to Europa. And launching the SLS will save you 4 years. You could get there in roughly 2 years. So you launch more mass, you get there a lot faster, you carry more equipment. So the point here is that having a big launch vehicle of the class of Saturn really enables some missions and makes an exciting future for exploration. Because you really want redundancy in spacecraft, you really like to have backup systems, you like to have more payload. If you carry more power, you can have much more sensitive and better instruments to do examinations. So it makes everything better when you can launch payloads that are heavier and faster. One of my favorite missions of all is Titan. Now, Cassini went around Saturn and examined Titan, and the Europeans flew along with us. The Huygens probe actually penetrated and touched down on Titan. But Titan is the only known body in the solar system and all the creation other than the Earth that has liquid oceans, probably hydrocarbon oceans, methane oceans perhaps. So if you had enough mass and you launched enough payload, you could conceivably land a lander on the surface of Titan, deploy a rover that drives to the seashore. It actually has waves and wind. Titan is a moon that has a dense nitrogen atmosphere. It's 4 times as dense as the Earth's atmosphere. It's pure nitrogen. So you could land a rover. That rover could drive to the shore, touch the waves, deploy a tethered submarine, and you could sail the oceans of Titan if you had enough mass in a launch vehicle. So that would be my favorite mission, to land a rover, deploy a submarine, and to sail the hydrocarbon seas of Titan. Now, it's incredibly cold. Incredibly cold. But if you have a lot of foresight and you have a lot of capability, you can begin to think about missions that you would never contemplate if you have to live with the present fleet of launch vehicles. That's obviously a far out mission, but it is conceivable if you have enough payload capability, and that's what we'll have with the SLS. Another great mission would be a mission to the moon of Neptune called Triton. A different moon orbits in the other direction. There's a lot of moons that are very different. That's one of the things Cassini learned at Saturn. Saturn has an extensive moon system. It seems they're all different. They're all strangely different. And so other planets like Uranus have extensive moon systems, but we don't know what's there because we haven't had a close-up view. Perhaps the moons at Uranus would be extensively different, very interesting to find. I've got 5 minutes, I think, so let's push on. I mentioned the big telescope, the monolithic one optic that would be 8 meters in diameter. The astronomers would love to have that. Nothing is to be deployed, 400 times the fidelity of Hubble. And you could look at planets and other solar systems. That would be a great mission for a heavy lift vehicle that had a big payload. Another thing that Brand perhaps might like is a turnkey space station. You could launch a 8-meter diameter habitat that's inflatable. It's 8 meters when it's stowed, but it deploys to 23 meters when it's inflated. And you've got enough mass to launch that as a complete space station. So when it inflates, it has everything. It has power. All you have to do is just ride a capsule up there, and you don't have to spend 20 years building a station. You can do it with one launch. That's an interesting space tourism in low lunar orbit. And as Tom will tell you in just a minute, you can launch the big vehicles needed to get to Mars. I think he's going to major on the Mars missions. Here's a Mars sample return mission, crewed Mars missions, and that is about where I am on the end of my thing. There's several things I wish I could talk about. I didn't have time, but if you have a heavy lift launch vehicle, you can do a lot of things. And I'm sure Tom is going to talk about some more. So how am I doing on time? Am I done on time? Okay, so who's got some questions for the stuff that I started? Yes.
I'm really impressed. NASA's done a great job with getting commercial launch capabilities going. How do you all feel about that? How does it be a part of this?
Well, let's back up to commercial. Those are only suited to launching to the space station, and so they're limited. Those capsules are to just that mission. The Orion is altogether different. It's for these missions to Moon and perhaps to Mars. And so there's 2 levels of thinking. There's the commercial systems for just the space station, and then there's larger systems for ambitious exploration. You don't go to the Moon in in a Dragon, or you don't go to the moon in a CST-100. That's the land, that's the purview of the Orion and the SLS. And so I'd like to see beyond lunar transportation, beyond lunar missions, not just the space station. We've been going to low Earth orbit since when, Brand? 1960, whatever. So it's time to go beyond, and this is what we have to look at.
So how does BFR fit into that?
Well, BFR, I don't understand a lot about BFR. Working at what I am, I don't do extensive competition analysis of the BFR, so I can't speak about it. I've seen pictures of it. That's the extent of my knowledge of the BFR.
So it's still a theory, not real data.
Well, we have a vehicle in production that's going to be tested in Stennis shortly, and it should be flying soon. So that's going to provide 130 metric tons to low Earth orbit, 45 metric tons to TLI, 35 metric tons to Mars. That's going to be significant payload. That'll do the missions that we have contemplated for the next 20 years. So we have the solution if we can deploy it and get it going, and so I think we will. So can't say more about the BFR. Yes, Phil?
Then there appear to be ferocious arguments ongoing as to what's the most desirable, most effective astronautic mission to Mars, Phobos and Deimos or the Martian lander. You must have some personal thoughts about it.
I do, Phil. It's a 3-year mission, so it's going to introduce a level of danger and complexity that you don't have on a 3-day transfer to the moon. And so some wise thinkers have said, let's go to Phobos first and not deploy a lander. The very first mission can be without a lander, so you could go sooner because you don't have to develop the lander, and you could validate all your transportation stages. Phobos, of all the moons in the solar system, is the closest to its planet. It's only 6,000 kilometers or so. And so you would have a very good view of Mars. Okay, one side is always facing Mars. And so Phobos would be a great introductory mission to Mars, and it would reduce the complexity of the first mission. You wouldn't have to fly the lander, which would save you years, and so you could get there sooner and demonstrate something, get that under your belt, then you could go to the surface. There's some wisdom in that. I don't know if that's NASA's baseline plan. It probably isn't, but it's being discussed. So that is a great question. I'm going to fall in the favor of the safer mission as the first mission.
That suggests that science that could be done is the ultimate driver.
Yes, you could deploy real-time autonomous rovers on the surface in which you actually drive them in real time. You could also explore Phobos, and Phobos may have some interesting features. Phobos has such a small gravity level that you don't land on Phobos. You kind of rendezvous with it. It has almost no gravity. So you just kind of park next to Phobos. You'd get out in one of Brand's suits and just fly around Phobos. So that is a great introductory mission. I like it because it's safer. I'm worried about 3 years. When you're that far out for 3 years, you could have some difficulties, and that would reduce the complexity somewhat, not totally, but I'd love to see a mission Phobos first. But yes, in the back.
Once you have the space launch system proven, what kind of production rate do you see for the different vehicles so that you can have multiple missions in a year and so on?
Yeah, that would be a function of the amount of money allocated to the program. I could see 3 launches in 2 years as a baseline, perhaps, and more money would produce, more throughput. But that's a good question. It's really ultimately up to Congress to allocate that funding, and I think the funding would support 3 every 2 years, or yes.
So you'd be able to ramp up production, so to speak. You'd be able to ramp up production if...
Yes, ramp up production, definitely, yes.
If Congress said, let's send a bunch of people to Mars, and it requires...
Yes, you would need a surge capability beyond 3 every 2 years. You would need 7 to 8 in 3 or 4 years. So yes, you would have to develop a surge capability for that. Okay, anybody else? Did I answer? Yes, sir.
What's the duration of the stay at Phobos?
At where?
At the moon?
There's 2 approaches. You can stay for 60 days on what's called an opposition profile, and if you go on the lower energy conjunction, it's 500 to 600. The longer stays, you're waiting for the planets to be realigned, so you have a minimum energy return. So if you want to save propellant, you would end up waiting that year or 2 years. I prefer the opposition, the von Braun team in the 60s, for crew safety reasons like the short stay. I mean, 60 days is a lot of time to do things on the surface. But it also has to do with the amount of time you're in space. You're actually traveling in space longer for an opposition profile. So if you talk to my friends at JSC, they prefer the conjunction because they believe it's safe on Mars. It's safer than being in space. So there's still some debate on that, but most people would side with the conjunction. I believe Tom would probably side with the conjunction. Yes, 600 days on the notional mission for staying on Mars. You're required to stay that long before you can leave, and that's a limit. That's a constraint, not a privilege. You have to be there. You can't leave early if you fly that profile, right?
It's a constraint and a privilege.
Yes, a privilege.
How many days was that again?
About 600 days.
100 days.
600 days, yes. The synodical cycle is 2.2 years long, and so you're always going to wait until the Earth, Mars are aligned so that you have an easy return. And there's some really hard returns. You would never be able to build a spacecraft that could carry the propellant needed for a non-aligned return. So that's critical when it comes to designing vehicles. So you've got two choices, 60-day or 600-day. Yes, sir. Ellis.
So I know that von Braun had a Mars plan.
Yes.
He was promoting in '69, and he had, a shuttle, a space station. You were one-man spacecraft that he was going to use to assemble the space station, and then he was going to have two spacecraft, as I understand it, traveling from the space station to Mars.
Yes.
He thought he could get to Mars by '82. And was that just totally out of the question, or if we kept funding it at 4% or 5% of the budget? I mean, you may not have any idea, but if we had the same level of funding for that as we had for Apollo, could we have done it 30 years ago?
That's too big a question for me. Brian, why don't you take that?
Maybe. I don't know.
Well, another thing is that the Saturn V was built for production. So if we were to keep on producing it, we would have the heavy lift launch vehicle, large diameter. I think, though, all of us have studied Mars quite a bit. It's not an easy mission. So, on the surface, he may have been able to say that, but you would have had to have had, I think, an Apollo-like mentality and urgency to make it happen. And I don't, yeah.
And funding.
Yeah, well, I was wondering if you kept 4 to 5% of the. Yeah,
You can't
that
say
would've
for
been
sure
happen.
that would, but it's almost for certain that it'd be impossible without it at that time.
Yeah.
And you really still would need to drive out your technologies on the moon and test them out before you tried to go live on Mars or go to Mars. And so visiting the moon versus spending considerable time is different. Yeah.
Well, we're going to have to move on to the next presenter. Thank you very much, Ben. Well, we've been talking propulsion, and we will continue in a little bit, but we're going to take a wonderful break right now, and we're going to talk about in-space manufacturing. This is an exciting area, and it's an emerging area, and it's an area that can change the dynamic of space flight and what we do. Nikki Werkheiser is NASA manager for in-space manufacturing, responsible for developing the on-demand manufacturing, repair, and recycling technologies required for sustainable long-duration space missions. She was instrumental in launching the historic first 3D printer to manufacture parts in space, as well as in-space recycling, bioprinting, printable electronics, and more. Ms. Werkheiser has spent the majority of her career in NASA's Space Shuttle and International Space Station program payloads offices, where she designed, developed, integrated, and operated multiple NASA payloads. Ms. Werkheiser has a Master's of Science from the University of Alabama, Huntsville, in addition to a Bachelor of Science in Biology and a BA in Russian Studies. Nikki Werkheiser.
Okay, is everybody still awake out there? Okay, I'll try my best. I know we're probably getting close to snacks and bio breaks. So first, though, since we are talking the future of space exploration, I want to take just a minute and express my most sincere gratitude for the space legacy that we've been gifted. And truly, I use the word gifted because that's exactly what it is. We had really audacious, relentless individuals in the pursuit of what was considered impossible and making that possible, many of which are right here in our own city, some of which I'm going to embarrass tonight and say are right here in this room. Dr. Bob Nautman, he's one of my heroes. So I just want to take a minute to say thank you to them, because that's what really propels me, and I'm sure many of you, in what we do every single day. So I'll try not to cry when I say that, but I'll go on and talk about what I absolutely love doing every day and why I'm so excited about it. So in space manufacturing, of course, we all know that means 3D printing in space. You'll hear me say 3D printing in space a lot, but I'm trying to break myself of that. I'm trying to say on-demand manufacturing, or come up with another clever NASA acronym that sounds really cool to get that across, because while we are using the benefits of 3D printing proper, really we're using a lot of hybrid manufacturing, so additive and subtractive, mixed with some pretty cool novel technologies that you may not hear about yet or behind firewalls, and which is some of my favorite part of my job, which is working with companies and in academia kind of behind the scenes as well to leverage what they're doing and adapt it for space. So let's talk first about what is 3D printing. Most people here probably have seen it. How many people are familiar, have seen the printers around all the various stores, and how it really works? It works actually a lot like a paper printer on the ground, right? So a paper printer that lays ink, dots of ink, based on an electronic file that you send it. We don't think about it much anymore. We just send it from our computer and it happens, right? But we're sending that design file and it's printing the dots where we want them. So a 3D printer works the same, except of course it's three-dimensional, and it's laying dots of plastic or metal, and it's building those up based on those instructions, those electronic instructions or CAD files that we're sending its way. And so we see a lot of things in the news now. You can make cool gadgets, right? Phone cases, jewelry, all kinds of cool stuff. There's a lot of things that people don't know as much about that 3D printers are doing now. Oak Ridge National Labs 3D printed a Shelby Cobra. It's pretty sharp. They have that on display. 3D printed food. How many people would eat a 3D printed steak? Chicken nuggets? Any takers? Anybody? Nobody? Bueller? So in all seriousness, though, the model we use on the ground today to make meat and grow our meat is really not super sustainable. There's a lot of issues with that. So using stem cells to 3D print meat on space missions and on Earth, as well as 3D printed organs. We all have heard probably in the news of vascular, cardiac tissue, livers. So there's a lot going on in that area as well. Shoes. This is one that my youngest daughter cares a lot about. How many people have teenagers? 3D printed shoes. I'm wondering if they can get the price down if we can 3D print those suckers. But that's happening, and we're actually making very customized products such as shoes using these capabilities. And prosthetics. This is a huge area, obviously very customizable, and really can do some amazing work and create amazing products with prosthetics. And then just custom tools as well. So, think about what you would 3D print, and then we'll talk some about, but why would NASA need 3D printing? Now, that's a rhetorical question, right? Because it just seems to go together very well, like peanut butter and jelly. But the bottom line is, we've been talking about the moon and Mars. We're going to be much further away from Earth than we are with space station. And the model that we use today on space station for consumables and repairs and maintenance, it simply is just not feasible when we get further away from Earth. So we do need a paradigm shift. Remember, the ISS is about 250 miles away from Earth. Takes a few hours to get there. Talking about the moon, I think we're at 3 days or so, right? Which is still considerably different than a few hours. And of course, it's about 240,000 miles away. Now, the average distance of Mars is about 140 million miles, but the closest we can get around, 35 million, so give or take a few million. And then we're looking at several months. So that's way different than a few hours to space station. I don't know about y'all, but if I go to the beach, it is just absolutely inevitable that I will forget my sandals or my sunglasses, and I end up at Walmart. I cannot imagine trying to think of everything we're going to need for a mission to live on the moon or Mars, for consumables and repairs and everything that could break. It's just not feasible. Not to mention, we really want independent off-Earth living. We want the astronauts to be able to make what they need, when they need it, wherever they are. And when I say that, do I mean the astronauts are going to be sitting around designing parts? No, we're probably not going to do that. But we will have people on the ground, teams of people developing and designing parts and uplinking them to the crew. So it's a very meaningful capability. And our motto that I like to say is make it, don't take it. I will clarify there, people see me coming and they think, oh God, she's going to want to 3D print everything, she's going to take it over. No, I don't tend to say that this works for everything, but where it makes sense, it makes a lot of sense. So that's what we're doing now, is our team not only works with industry and academia to take those technologies and capabilities being developed and adapt them for spaceflight, but we're also working with our exploration system designers within NASA, our life support systems, our crew suits, we got to talk more, our tools, of course, our crew health systems. Crew health is endless opportunity for this area for a couple of reasons. One is many of the types of scenarios we'll have to plan for if we're living on the moon, we've just never really had to deal with on station. We would come home, right? Think of dental care. If you have a really bad toothache and you're that far from home, that's really something you have to address. Fortunately for us, for NASA, the dental industry was one of the earliest adopters, not only of 3D printing, but also of the diagnostic tools like scanning. So we can use that pretty easily and adapt that for space as well. So it's kind of an endless opportunity in terms of crew health and medical. Things like splints we have to prepare for if we do have sprains or breaks. A lot of the video you see from the moon, you'll see a lot of tripping and falling. If you think about a mission to Mars, you're going to be traveling for months in microgravity, and then you're going to be back in gravity. You're going to be quite busy trying to get everything set up. So you can imagine that sprains or fractures could be a real possibility. You're not going to want to really deal with the old-fashioned plaster casts. So here on Earth today, people are designing customized, very sterile, breathable, kind of cool looking, kind of artsy casts and splints and things. So lots of kind of endless opportunity there as well. So our current ISS resupply model, as I mentioned, is just to keep shipping stuff up, right? And we keep about 98 to 99% of our consumables and maintenance items and high-risk failure items on the ground at any given time, ready to go, but they're on the ground. That's not going to be a feasible model for long-duration space flight. In addition to that, the way we design our backup parts now for our larger systems, like our life support systems, is called an orbital replacement unit, or an ORU, because we're NASA, so we have to have acronyms. So ORUs, we don't really focus, like if something goes wrong on ECLSS, we don't really focus on orbit of trying to diagnose that exact component that broke. They'll take out that whole ORU and they'll bring it back home. The experts on the ground will study it, take it apart, figure out, oh, is this valve, it was this seal. They'll fly up another ORU in the interim and then figure out how to fix that for the long duration. That's really not feasible either for longer duration missions, to have the ORU mindset. What we're really trying to do with in-space manufacturing is get involved in that design process and do what we call design for maintainability. So making the areas that we need to work for consumables or maintenance items or high-risk failures accessible, and then being able to 3D print those, right? Or on-demand manufacture them, I should say. So the space station is literally a one-of-a-kind test bed in the entire universe, right? So not only are we doing amazing science and learning about living in space for almost 20 years now, but as we look at our long-duration spaceflight missions coming up quickly, I hope, then it really is a one-of-a-kind technology test bed as well. When I say technology, of course, we think about the lack of gravity, but it's more than that. When we look at space operations, we are always going to be limited to some degree with mass and with volume and with astronaut time and worrying about failures and how we get things taken care of in an efficient manner. So we're always going to be limited there, and so station is a way for us to create these systems, what I call our first generation exploration systems, and test them out in that environment. And then we'll use those technology demonstrations to springboard into our exploration missions with our first key capabilities. And that's what we do in space manufacturing. So we cover quite a bit of area. We do work not only the on-demand manufacturing, but the repair and the recycling, which I'll talk about in a minute, which is a key component, and reuse of materials when we look at long-duration missions. So we're looking at things, everything from plastics, which is what we started with, and we'll talk about next. It's kind of the lowest hanging fruit, to metals, of course, to printed electronics. It never fails. How many teenagers do I have in here? Not many. I always get asked, when can you 3D print my iPhone? So we're working on that. And then, of course, we touched a little on in situ materials. So when we're on surface destinations, we really want to be able to use the in situ resources as much as possible. So when they talked about mining oxygen, we're also looking at mining metals in the regolith for manufacturing processes as well, and trying to make feedstock. So let's talk about this one for a minute, because many people here will remember this directly, Apollo 13, and others will remember it by Tom Hanks and Apollo 13. But everyone, I think, has probably heard of the square peg and the round hole, right? And so we all know the heroic story about the crew had to move over to the rescue ship. Their square carbon dioxide filter did not fit in the round barrel of the rescue ship, and so this heroic ground crew kind of figured out a way day and night to cannibalize parts and come up with a solution. But it's kind of fun to think about what would have happened if that crew had had a 3D printer, right? So a company we work with called Made in Space, that I'll talk about in a minute, that we flew our first 3D printer with. They're out in Ames Research Center in Silicon Valley. And they had a high school intern. So they brought him in. He was a pretty young guy. I don't even think he had seen the Tom Hanks movie, to be honest. And they told him and kind of familiarized him with the problem. And he had some basic kind of CAD designing skills. And they asked him to think about how he would have designed a solution for this, just to see what happened. I want you to know that within one day, that young man had not only designed a solution, but he had actually printed it. And so I stop and I think for a minute how amazing that is, that this young individual was given a technology and a skill set that was able to solve what was originally a life-threatening technical issue with this new capability. And I think that's really cool. So we're looking at how NASA can do the same thing in space. So we built an in-space manufacturing roadmap and talked about what the first logical steps were. And I mentioned that plastics were the first logical step, right? And we think we thought that process would work basically the same in space as it does on the ground. So we worked with a company, Made in Space Inc., and through a Small Business Innovation Research Award. And in 2014, we launched the first plastic 3D printer. It was pretty small. I don't think I actually have a picture here. It's about this big because it had to fit into the microgravity science glove box. Why, you say? Well, it was the first time we were making parts in space. So when we had our safety review panels, they were very interesting. We spent a lot of time in philosophical discussions about how this part that I was showing them was not the actual part that was going to launch. The part that we would make up there would be just like it, I promise, but it wasn't the exact part. So that in itself is a philosophical change, right? Showing that how do we know that even if we make it 1,000 times on the ground, it's going to be made the same way there? How do we verify that? If you're not working structural parts, I mean, it depends on what you're making. It's not as big of an issue, but certainly for structural parts, that's key, and we'll come back to that in a minute. So we did fly this printer, and I'm happy to say it was a successful experiment. We were able to print. We brought the 55 specimens that we printed back to Marshall Space Flight Center, where we tested and analyzed those in great detail. Lots of fun publication reading on the NASA Technical Repository server on all those results. And we found that it works the same way in microgravity as it does on the ground. We were able to print the same quality of parts. We also experimented some, for those who have worked a little with 3D printing, if you have overhangs, and of course this pesky gravity thing, you have to build supports and then take the supports out afterward. We were actually experimenting with, without gravity, how much fun we could have with that, right? And do we really need supports, and what kind of cool things could we do? So I don't want to always look at microgravity as a challenge. Sometimes it's a real opportunity as well. I'll also say that we emailed our first part to space. Now, okay, we all know we didn't really email it, but I like saying that. We uplinked the file. It is the first part that was ever made in space that wasn't launched from the ground. And so we gave the team on the ground a challenge. We only gave them 2 days. We didn't tell them what the part was going to be. And we gave them 2 days to get it designed and uplinked and printed on Orbit. And that's Commander Butch Wilmore holding it there. It was a little ratchet. This one's a unidirectional ratchet, but it was all printed in one part, including all the gears. And the file, just for fun, if anyone is interested, is on the NASA 3D Printing Resources website. And if you go to YouTube and type in NASA 3D Printed Wrench, you'll see tons of people on the ground have printed these and played with them and kind of compared them to the ones in space in different colors, so that's kind of fun. And then I'll talk about the next step. The next step, we learned what we did from 3D printing, worked with Made in Space. They infused those lessons learned into the additive manufacturing facility. I should have mentioned the first 3D printer printed with ABS plastic, which most people know because of Legos. They hurt if you step on them. And the one we have up there now does 3 polymers. It does ABS, it does Ultem, and it does high-density polyethylene. The interesting thing about AMF, of course, it's a larger printer, it does 3 plastics, but it's a commercial facility, meaning that NASA is one of the users. We did help fund and enable this through small business innovation research contracts, but we're just one user. Industry, international partners, academia, anyone can use AMF and make things in space, so that's kind of cool. We've made several things I know I don't have time to go into, but I could talk about for hours that we've tested and designed up there. And every time we design and use something, we learn something new about that design process and the use of these capabilities. So let's talk trash for a minute. So on the International Space Station, we all know these fun pictures we see, there's a lot of trash, right? And they pack it all up. At any given time, we have about 2 metric tons. And they pack it all up and they burn it up. That little image at the bottom is them burning it all up, right? So you look at that and you say, wow, for exploration missions, I don't really want to throw all that stuff away. How can I use that? We're talking food packaging, medical waste, things like syringes, things like the little otoscope specula that the doctor pops out every time you use them. I think they test out the crew's ears every couple of weeks, and they fly hundreds of those suckers and throw them away after one use because there's not really a good, easy way to sterilize them right now. Packaging, of course, escaping gravity, and that takeoff's pretty rough. We have to pack everything with foam, and we just burn that foam up. Plastic bags, affectionately known to many of us as Ziplocs. We have thousands of them. So there's a lot of potential materials for reuse, which is why we now have what we call the refabricator, and we call it the refabricator because, as far as I know, it's the first ever integrated 3D printer and recycler all within one machine. This is also done through a Small Business Innovation Research Award with the company Tethers Unlimited Inc. in Seattle, Washington. And they actually created a very novel new process for recycling. Most commercial recyclers on the ground use pellets and they grind them, and of course that causes a lot of material shear. And so you don't know how many times you can recycle without getting a lot of degradation of those parts, right? Well, they actually created a process where you extrude the filament. They call it pos-extrusion. And it's very consistent, smooth filament, and they have a bonder, which is a new technology they created that actually bonds the filament in pieces together and then extrudes it down into the printer and spools it, and then you print with it. So this is actually on Space Station right now. It's about the size of a dorm refrigerator or 2 mid-deck lockers, as many of us would say. And we're doing operations now. We're learning a lot from this already. We have pretty much a plastic block that's been recycled on the ground that we start with. Put that in there, and it creates filament. It prints 5 tensile specimen, and then it reprints that block. The crew takes those specimen, puts them in a Ziploc bag, puts the block back into the refabricator, and it does that 7 times so that we can study over time and then see if we see any degradation or any differences in what we're seeing on the ground. You might imagine this would have amazing potential right here on Earth. Imagine if you had a machine like this, about the size of a red box or smaller, outside of your grocery store, that you could put in water bottles. We've done this with water bottles, Ziploc bags, garbage bags, and it would make 3D printed filament you could print with. Or you could even have custom designs in there for cell phone cases or jewelry or whatever you can think of. So it's kind of a neat model to think about how we would use that on the ground. So what next? As I mentioned, I could talk for hours, and I think I only have 1 minute left, and there's lots to come next. But I do want to mention the other thing we're working on now is called the Fab Lab. That's our short, affectionate name. It's the Multi-Material Fabrication Laboratory. It's our first shot at metals. Metals are a lot more challenging. Obviously, on the ground, we use a powder bed process, a laser powder bed. The powder's very, very fine. Not great for microgravity, very combustible as well. As I mentioned, though, there are a lot of companies working on how to take these metal processes and make them more marketable on the ground, which means smaller, more portable, not as much facility and resources and people they have to use. So there are some really cool hybrid processes. We competed this about a year or so ago on a public-private partnership, broad area announcement, and awarded 3 companies to try to build the phase A of this, where we'll have a preliminary design review and a prototype built. I'm happy to say that they are ahead of schedule and is extremely promising. It'll be about the size of a double refrigerator like at home, but for that you actually get aerospace grade metals. That you can has inline inspection capability and autonomous or remote part removal. So it's a pretty amazing capability that I think would have phenomenal potential here on Earth as well in the commercial market. Of course, we're doing a lot with in situ resource utilization. We work closely with that team and looking at things like how we would do additive construction. Right here at Marshall, we have a machine that actually is using Portland concrete right now, but can also use Martian or lunar Regulus simulants to build habitats in large structures. You've probably seen some things in the news about people building small houses for things like FEMA and the homeless. A lot of potential, a lot of work going on in this area as well, and we're testing that out here at Marshall. The 3D printed electronics, and as well as wearables, as well as wearables for crew health. We're actually doing biosensors for cortisol and all sorts of different things right now for kind of wearable printable electronics. And then we also have several activities going on with our large external structures in space, where we're actually 3D printing beams and arrays and things like that on the ground. We've already went through thermal back testing and then plan to demonstrate those as well in space, hopefully on station soon. So I could talk about this for a lot longer than any of you have, and I love doing so, but questions are my absolute favorite part. So I try to just give teasers and then move on as quickly as possible to questions. So what you got for me? Yes, sir.
If we were starting to build a lunar outpost tomorrow, are we ready to start using lunar soil to?
No, sir. I think we are ready to start learning more about how to use it. I think we have a good basic foundation, but there are things that have risks, as such as right now, for example, simulants that we're using are not all consistent. You know, we're having discussions about how to have standards for the simulants that we're using in testing. We could have a false sense of security if we're using improper simulants and we're testing and it's looking great, and then we get there and the actual regolith is different, right? So there's a lot of thought process there and a lot going on in this area. I certainly think it holds a lot of promise, and the roadmap for the ISRO area will start first with water extraction and oxygen extraction from regolith, and then start extracting as well metals and other byproducts for manufacturing. But we'll also be using that fab lab that we're using in transit on the surface and adapting that to be able to use any regolith-based feedstocks that we develop as well. So lots to do still. Yes, sir?
If I think about old school ships out at sea trying to repair stuff, they have machine shops as well.
That's right.
So in terms of processes for metal stuff, are you heading in that direction, or are you just printing, or is it a combination?
Yes, it's a combination. We're starting with the fab lab. We also have things like friction stir weld that we're talking about, and you have different applications, of course. We're starting kind of with the what do you need at a bare minimum. At a bare minimum, you want to have metal capability for large structures, for external type manufacturing, and then some inside too for tools and a lot of biological type materials that you would never want to use plastic for, those sorts of things. So that's why we're starting with the fab lab, and we started with our tipping point proposals I mentioned for the external in-space manufacturing. The good thing is we can benefit from nanotechnology and the downsizing a lot of these capabilities, and as I mentioned right now, we're on a real kind of renaissance or precipice with the metal processes. I don't know if you're familiar with companies such as Desktop Metals. If you Google them, they have a really amazing machine that's an office-sized machine that can make high-quality metal products. They spun out of MIT, I believe. And they're using things like, in the design, they're using biological algorithms to help, too, in the design process. So you pretty much say what your structural property objectives are, and then these algorithms actually design the part for you and optimize the machine to print it. So there's a lot of kind of cool work going on in that area. The ones we're working with are hybrid. It is additive and subtractive. And so we are, talking a lot about post-processing and inline inspection, and that is part of our Fab Lab prototype.
I guess the other area, nowadays electronics fail.
Hmm.
Either one, Navy ship, they fix that. Have you done any experiments trying to change a chip or a part on a certain board in orbit or?
Not in orbit, but on the ground. So we have we have a printed electronics team here at Marshall and at Ames Research Center that are working very closely together as part of the project. We're about 3 years in. We're printing multifunctional sensor boards and platforms that we can actually use for a multitude of purposes. We're working with our crew health systems on the flexible electronics, as well as our groups like our RFID antenna folks and RFID communications. And printing those with Bluetooth-enabled printed capability and trying to get those all printed on one board. So all of these, like the Fab Lab, will be capable of hybrid materials. So most of the electronics we look at, we would embed the electronics into usually a plastic or possibly a metal. And so we're working on that right now as well. We're working with industry as well as the teams at Marshall and Ames to test those out. Our next step would be to test those on orbit. We actually just received delivery of a plasma jet printer that we think would work very well for in space. It's very safe. It's a low power. Actually, when it was printing, I could actually put my finger in the plasma jet. It's room temperature. It's pretty wild stuff. It's a company called Space Foundry out in California. Oh goodness, yeah.
We have time for one more question.
No more questions?
What's the smallest dimension?
Oh, gosh.
Can you print like CPU for computer lithographics size?
Yes, we can do we very small. I can show you some things afterward too as well. You had one over here?
You may not be the right person for this. Were they, the electronics are progressing at such a fantastic rate. Are they doing anything in the realm of, designing satellites where you can replace the electronics going,
Yes.
years down the road?
Actually, it's a great question. So we've actually been working pretty closely with DARPA on a project very similar to that. DARPA's doing some outstanding work. And the other kind of cool thing about when you think satellites, even things like CubeSats, with nanotechnology, you can do so much more with CubeSats. The only issue right now is we have to launch those, so you have to survive launch loads, which means you have to make them, the structure pretty heavy. If we can actually print that structure in space, which is something that Made in Space is working on, you can kind of use more of a honeycomb type structure, and you have a lot more room for instrumentation. And then with software, you can actually evolve even the functionality or the capabilities of the satellite over time by just uplinking new software. So it's a whole different kind of thought process. Yeah, evolvable, I really think, yeah. Thank you so very much.
Okay, thank you. Well, you've got a treat coming up. Dr. Percy is a great presenter, and he's got a great message, and you're going to hear some stuff about Mars that really addresses the future and what this panel is about. Dr. Percy currently serves as the mission architect for the Advanced Concepts Office at Marshall Space Flight Center. Tom primarily has been involved in advanced in-space transportation, including advanced propulsion technology development, trajectory analysis, spacecraft, and mission concept development. Prior to his time with the Advanced Concepts Office, he analyzed emerging propulsion technologies for the In-Space Propulsion Technology Program Office at the Marshall Space Flight Center. He holds a PhD in Aerospace Systems Engineering from the University of Alabama in Huntsville, a master's degree in Aerospace Engineering from Georgia Tech, and a bachelor's degree in Mechanical Engineering from Rochester Institute of Technology. Tom Percy.
See if I can get this to stay up here. Thank you all very much for having me and for coming out tonight. I'm supposed to be talking to you about how we're thinking about sending people to Mars. So hopefully you'll enjoy the presentation. So this is Mars. Okay. I'm sure we're all pretty familiar with what it looks like. It's fourth planet from the sun. A year on Mars is about 687 days. A day lasts 24 hours and 37 minutes. The average temperature is about minus 80 degrees Fahrenheit, but in some places it can get as balmy as 70 degrees Fahrenheit. The atmosphere is about 1% the density of Earth, and it's dominated by carbon dioxide. And the gravity there is about 3/8 what you'd feel here on Earth if you were there. And Mars has had kind of an interesting history with the development of science in humanity. About 400 years ago, the odd motion of Mars across the night sky actually inspired Johannes Kepler to go and rewrite all the rules about how planets orbit things. And those rules still apply today. They're the same rules that we use to develop trajectories and determine where satellites are going to be in the sky. About 125 years ago, Percival Lowell read about Giovanni Schiaparelli's canale on the surface of Mars, and he took his fortune to Arizona and opened an observatory just so that he could map them. And then other people read about what Lowell was doing, and they were so captivated by his idea of civilizations on Mars building things that they wrapped them into this new genre of literature, science fiction, that was just emerging at the time. And they created these wonderful worlds like Barzoom and captured the imagination of generations of people with these stories of little green men invading from Mars. Right? So Mars has actually played a pretty prominent role in our humanity's history. And over the last 5 decades, we've spent a lot of time sending robots to Mars to start to see what we can find there. Those missions started off pretty small and simple with a flyby of the Mariner 4 spacecraft. We got a little more aggressive and landed the Viking probes. And then fast forward all the way to the last decade to 2 decades, and we've had quite a bit of success in robotic exploration at Mars. In fact, today, there are 8 operational spacecraft, either in orbit or on the surface of Mars, and they're run by 4 different space agencies. And we have plans to send 5 more in 2020. So we've got this kind of revolution of robotics at Mars. Now, one of the things we've done with robots at Mars is we've sent rovers. We started very, very small. We've kind of progressed from there. In fact, the Opportunity mission was just declared a resounding success a couple of months ago. Opportunity spent 15 years on the surface of Mars and traversed 28 miles. And that was pretty good for a spacecraft that was designed to last 90 days and go a mile, right? The latest entry in the family of surface rovers on Mars is Curiosity, the picture you see here. Now, Curiosity is roughly the size of a Volkswagen Beetle, weighs a little less than a metric ton, it's nuclear powered, and it carries a full complement of science instruments that are helping it research the history of water, geology, and climate on Mars so that we can try to answer the question of whether or not we think Mars was ever capable of supporting life. Right? The robotic exploration of Mars has contributed a lot to what we know about planetary science and what we know about the red planet. We still want to send people. Right? And why would we want to do that? It's a much harder job, right? Well, Steve Squires, who was the principal investigator for the Spirit and Opportunity missions, and many people consider him to be the father of roving science on Mars, has stated that while Spirit and Opportunity have done wonderful things for science, they operated for a collective 22 years on the surface of Mars, the things that they did could have been accomplished by a small group of well-outfitted people in a couple of weeks, right? And the reasons for that are twofold. Their specificity of investigation and an overabundance of caution. Right? Driving a rover on Mars is not like driving an RC car in your backyard. It's not even like flying a UAV halfway around the world. All these radio signals travel at the speed of light. And that means that at times it can take up to 40 minutes to have a round-trip conversation with Mars. 20 minutes for a signal to come in from Curiosity with a picture, and 20 minutes for us to send back a command for where it can go. So there's no real-time driving on Mars right now. And so we drive very slowly, right? Curiosity's been on Mars for 6 years. It's gone a whopping 12 miles, right? It's not exactly the fastest thing in the universe. And the reason we do that is because it takes a lot of money and a lot of time to get these robots up there. They're expensive, right? And the last thing we want to do is drive them off a cliff or run them into a rock and break them, right? And so we proceed with an overabundance of caution. We want to make sure that these things last and do their job. We also know that mass is a premium on these kinds of missions, and so we get very specific about the kind of science we want to do with these robots. And because we're specific about the science, we tailor our instruments specifically to address the questions that this particular mission is out there to answer. Now what happens is if we're driving along with Curiosity and we see something we didn't expect, well, that's nice and all, but we don't have the instruments to investigate it. So you guys better get on building the next rover and spending another $1 billion to send it out here because we don't have the right instruments, right? That's the specificity of our investigation. We're very specific about what we want to do. So we'd like to send humans because humans are adaptable. Humans can pick up a rock and understand what it looks like. Humans can make real-time decisions. Humans can do more in-depth investigations with limited tool sets, and they can just learn more and move faster. And they'd be a nice step up from what we're doing with robotics, right? So we want to make sure that we understand what humans can do, but we also have to figure out what it's going to actually take to get them there. Let's go to the next picture. So here's a nice picture. We want to send these explorers into space, right? The practical answer to why send humans is they can do better science, right? The dreamer answer is this idea that people are going to expand our horizons into the cosmos and we're going to become a multi-planet species and we're going to do more exploration because it's part of our humanity DNA, right? And honestly, I kind of believe that that's true. And we are going to expand our reach into space, and Mars is really kind of what's next, right? We've been to the moon, we're going to go back for longer, and we're going to learn how to do things there, but Mars is the next step. It's the first time we'll leave kind of the neighborhood of the Earth, right? Now, this particular explorer is floating in the cupola of the International Space Station, just looking out the window, back down at home, which isn't all that far away, right? And what we want to understand is what is it going to take to leave low Earth orbit? We've been floating in low Earth orbit for over 30 years. Carl Sagan used to say, wading out into the shallows of space, right? We did it in the space shuttle, we're doing it in the space station now, and we want to know what is it going to take to break loose of low Earth orbit. Well, let's put the trip in perspective first, and you kind of heard some of this already. It's worth repeating. The space station is about 250 miles above our heads. It takes a couple hours to get there. When we sent the Apollo astronauts to the moon, they were 250,000 miles away. And it took about 3 or 4 days, right? When Mars and Earth are aligned to send people to Mars, they're going to be 250 million miles apart. And the trip is going to take 250 days. This is a big job. It's a big undertaking, right? But we think it's worth it. And so now we have to figure out what exactly we're going to do to get there, right? So part of the reason why it takes so long, and they're so far apart, but it takes so long, is because the motion of Earth and Mars are governed by the same laws that Kepler used Mars to write down 400 years ago, right? They're in orbit around the sun, and in order to get from Earth to Mars, we have to put our spacecraft in an orbit around the sun that intersects both Earth's orbit and Mars's orbit. And we have to time it right so that when we get there, the planet's there, because they're both in motion around the sun, right? So we know that it takes some energy to get onto those trajectories and get off of those trajectories, and the real trick is finding the right trajectory to make that work. So just a couple of pictures. People have proposed a lot of missions for Mars. Some people have proposed flyby missions. I don't know if anybody has ever driven to Disney World from here, but imagine taking the 12-hour drive to Orlando, driving through the parking lot, waving to Mickey, and driving home. Flyby doesn't really do it for me, right? Some people have proposed one-way missions. The job gets a lot easier when you don't have to worry about bringing the people back. It's kind of an untenable option for us at this point, maybe someday when we colonize. So we try to bucket these missions that we're interested in, the ones that let us actually stay at Mars, into two categories: conjunction and opposition. Opposition being short stay, conjunction being long stay. The upper left-hand corner shows you a typical opposition class mission. This is the one Ben was talking about. 600 days, you only get to stay for 30 or 60 days. The rest of the time is in space, and it usually requires a flyby of Venus, because we have to get some energy boost from another planet in order to catch up with Earth. That means we're getting a lot closer to the sun than we're really comfortable with. It also means that we're going to expose the crew to about 540 to 570 days of deep space environment, low gravity, zero gravity, lots of radiation. On the other hand, our conjunction class missions are about 1,000 days long. They're almost 3 years. So they're a lot longer than the opposition class missions, but they actually spend less time in deep space because they hang out on the surface of Mars waiting for the planets to line up again. And so we get to go to Mars. An opposition class mission, you're going to Disney World, you get 2 hours at the park. When you drive home, you have to go through New Orleans, right? In a conjunction class mission, I get 24 whole hours at the World of Disney, right? a year and a half of exploration on the surface of Mars. And then I get to come home when it's optimally aligned for me to do it. All right, so what's it going to take to get there? We've got these explorers. We want to send them on a 3-year journey to Mars. What's it going to take? Well, it takes a lot of different pieces. And the biggest thing for us right now is understanding that the journey of 1,000 miles really does start with one step, but our first step is a doozy. We've got to get from Kennedy Space Center into space. We have to move a lot of mass there to do it. We have in-space habitats, we have lots of supplies, we have lots of other things that we need to send to Mars, and so we need a really big launch vehicle, and that's what the SLS is going to give us. A space launch system is going to be capable of putting 130 tons into space. That's the equivalent of about 10 school buses. And it's got about the same volume as about 10 school buses. So not that we'll send your kids to space in school buses, but what we're going to do with this launch vehicle is if we want to go to the moon, we're going to take one of them. If we want to land on the moon for a little longer than we would have for Apollo, do a more aggressive mission, we'll probably take 2, right? If we want to send a crew of 4 to Mars for a 1,000-day mission, hang out on the surface for 500 days, it'll take somewhere between 7 and 12 of these launch vehicles. We have a lot of stuff to move, right? Now, a whole bunch of that stuff that we've got to put into space is propulsion related. In fact, about half of what we have to put into space is related to propulsion. Our in-space propulsion systems are the chariots that are going to get our people to Mars and bring them home again. And there's lots of different options for that, and we're pursuing several of them right now. There's advanced chemical propulsion, which gives us a lot of thrust and fairly good fuel efficiency, specific impulse. There's nuclear thermal propulsion, which gives us roughly the same amount of thrust, but twice the fuel efficiency, which is great because that means we don't have to bring up as much fuel. And then there's electric propulsion, which is kind of a different deal. It's low thrust propulsion, but you get to apply the thrust for a very, very long time because the fuel efficiency is an order of magnitude higher than chemical propulsion. They all have their challenges. Both nuclear and chemical propulsion are going to require cryogenic fluid management. They need liquid oxygen, liquid hydrogen to get that kind of performance. It's hard to store because oxygen and hydrogen want to be gases. Nuclear propulsion is going to need a nuclear reactor. Electric propulsion is going to need very, very large deployable solar power systems, multi-100 kilowatt sort of systems. And there are other ideas floating around out there for fusion drives and very, very advanced propulsion systems. They're so immature at this point that it'll be decades before we're able to field any of those. We're pretty sure we could field one of these technologies within a decade. Develop the technologies and get them ready to go. And so these are the kinds of things we're looking at for in-space propulsion. Of course, the more efficient they are, the more energy we can put into our trajectory and the faster we could get to the planet. But right now, we're constrained to those pretty long 200-plus day trips to Mars. So that's your in-space propulsion. That's over half of what you put into space, and of that half, 75% of it is propellant. So we're looking for higher efficiency things. Now the other thing we got to move is habitation. We got to have some place for the crew to live, right? And so that's this deep space hab thing that we're talking about. So I want everybody to think for a minute. What'd you do this morning when you woke up? Probably had a little breakfast, maybe took a shower, maybe you did a little workout, brushed your teeth. Show of hands, how many people breathed some air this morning? I'm hoping everybody puts their hands up. All right, so we have the Earth to thank for that, this magnificent planet that gives us the air that we need and the water that we need basically right here anytime we need it, right? It's also got the added benefit, it's got a magnetic field that captures all the radiation, so it protects us from galactic cosmic radiation and solar flares and those sorts of things. When we send people into space, we have to recreate that environment. We have to give them a little Earth to live in. And so what we've come up with is this idea of basically a 3-story house that gives them radiation protection, exercise equipment for zero gravity countermeasures. It gives them enough food and water and air to drink and breathe and eat for the whole trip. It even gives them enough space so they don't want to kill each other before they get there, because it's tough to be in a can with 4 of your best friends for a really, really, really long time. And what we do is we pack this thing full of our supplies. Like you heard earlier, we send a lot of rockets to the space station to resupply stuff, about 9 a year. That's not an option here. This is not a road trip to Orlando. You can't stop at Walmart and pick up the thing you forgot or buy more food or get more water. Everything's got to come with you. So we have about 20 tons of food and air and water and spare parts and feedstock for 3D printers and all sorts of other stuff, right? It all has to go with us. Right? And once we get there, we'd like to access the surface because the only reason the conjunction class missions are safer than the opposition class missions is because we get to hang out on this giant rock that kind of gives us some protection for 500 days and gives us some gravity to live in. And so we need a lander. Now, the tough part is landing on Mars is kind of beset with all of its own challenges, the biggest one being the atmosphere. The atmosphere is thick enough that when we go through it, the friction is going to heat up the spacecraft and we're going to need some thermal protection. But it's thin enough to not be particularly useful at slowing you down. And with lots of mass barreling through the atmosphere, like this isn't a road trip, this isn't even Lewis and Clark, right? Lewis and Clark got to forage and hunt for food, they got to drink water out of the streams, and yes, they got to breathe the air around them. We don't get that on Mars, so we got to put all that stuff on Mars too. We got habitation modules and rovers and science labs. We even have to land a launch vehicle so that we can come back at the end of the mission. So we got about 60 to 80 tons worth of stuff that we have to put on the surface of Mars to sustain a crew for 500 days. The biggest thing we've ever landed on Mars was our old friend Curiosity, and that was a little less than a metric ton. So what we're doing is designing landers to land about 20 times that, and we'll send 3 or 4 of them and set up that base camp. That lander has a deployable aeroshell. It's 17 meters in diameter. That's almost twice the diameter of the first stage of the Saturn V. Go out to the Space and Rocket Center, stand under the Saturn V, picture something 17 meters wide. And it has to be that big just to slow us down a little bit, and then we engage very large rocket engines to do supersonic retropropulsion, slow down and land us softly on the surface. Right? So all that stuff gets delivered with those landers, kind of looks like this. This is that 7 minutes of terror thing that you hear about with robotic probes, but on steroids, because these things are enormous. I mentioned we have to get back into space. Our spacecraft will wait in orbit for us while we go down to the surface. We don't bring all that stuff to the surface if we don't have to. And so the habitat and the in-space transportation will wait in orbit. We've got to get back to it at the end. So we land this Mars Ascent Vehicle. It's basically a 2-stage launch vehicle that we have to land on Mars, prep, and launch without any of the infrastructure you have at Kennedy. And oh, by the way, fully fueled, it's too heavy to land. And so we have to use in situ resource utilization to pull carbon dioxide out of the atmosphere, turn it into liquid oxygen, and produce 78% of the propellant we need to get off the surface. But we can do that. It's a pretty straightforward process. It's 200-year-old chemistry, and we know how to do it. We just have to have the power and the systems to be able to make it work. So we do that, we fuel it up, we put the crew in that little cabin there, and then they stand shoulder to shoulder for about 2 days. And they get to fly off the surface of Mars and go back to their habitat and fly home. So what are we going to do while we're there? Well, this is kind of the crux of it, right? At first, it's going to be mostly the same kind of science we're doing with robots. We want to learn about the geological history, the climate, the water history. But we're going to be able to do it over a much wider range and much faster because we're going to have pressurized rovers that drive us out to far-reaching places from our base camp. We're going to have habitation modules. But we're also going to have lab modules. So we can do in-depth science on the surface of Mars. We're also going to have a power system, about 50 kilowatts worth of power. It's going to be delivered in 10 kilowatt chunks in a system called Kilopower, which is a joint development between NASA and the Department of Energy right now. Fission reactors on the surface of Mars generating that power for us. And then eventually we'll progress to some more aggressive things like learning how to do agriculture on the surface so we can be more self-sustaining. If eventually we do want to find a way to colonize Mars, we're going to have to figure out a way to live there without bringing all the stuff from Earth. We're going to have to find a way to do it there. And we'll be working right alongside those same robots that we had before. They'll be able to do work with us while we're there, and they'll be able to continue the research in between crew rotations. We can only get to go to Mars once every 2 years, once every 26 months or so. And we're gonna send crews maybe once every other opportunity just to make sure that we have got the supplies and the equipment that we need to do it. So there'll be some time when this is untended, and that's when the robots come in and help us take care of systems and keep doing the science while we're not there. So this is Mars. It is very much not like Earth, but on the list of all the places to go in the solar system, it's the next most hospitable place for people. And it's the next place that we want to go with humans because that's what we do. We explore, and that's where we're going to go. So wanted to thank you guys for your time, and I'll take some questions.
Is any of the mass that you save is based on taking everything, or can you make it with the materials you find there?
So initially, for a lot of the same reasons that we're not going to do our first lunar habitat with printing, we won't be relying on printing to get us the things we need. We're going to do in situ for the propellant production. We may even be able to do it for some breathable air, but not right away because we want to make sure that it's ready for prime time. We want to learn something about the regolith. It's super different than the moon. And unlike the moon, we've never brought anything back from Mars. So we really have very limited information about what it is and how it works. And so when we're printing with Martian regolith sample or simulant here on Earth, it's kind of our best guess as to what it looks like, right? At least with the moon stuff, we brought some back. We kind of know what it looks like. So we're not going to rely on it right away, but it's certainly a way to find an opportunity to be more self-sustaining as we progress through the mission. And eventually it can start replacing some of the things that we send. Habitation modules, if we can print something and just inflate a liner inside of it, that's going to save us a huge amount of mass. And so while we may need 3 or 4 landers the first few times we go, as we advance things like in situ manufacturing and those sorts of things, we'll be able to back off on that and maybe get to a point where we're only sending 1 or 2 landers each time. So, yeah.
Is the space elevator feasible?
Is the space elevator feasible? Theoretically, yes, absolutely. And just like Earth has a geosynchronous orbit where you can put something in the orbit and the orbit velocity is such that it matches the rotation, you can find one at Mars. And it might actually be a little bit easier at Mars because the atmosphere is thinner. But there's still a long way to go on materials technology before we can actually get there. I know carbon nanotube technology is going to get us pretty close, but it's still a long ways away. The real trick is, for those who don't know, space elevator is you put a station in orbit, stationary over a place on the Earth, then you tie them with the tether, and then you run up and down it, literally like an elevator, and you get to save all that energy that you would normally expend in a kind of inefficient chemical rocket like we do now. It's the materials that are really going to get in the way for that. So it's coming, but it's going to be a while. Yeah.
Are we ready right now, confidently manage for 600 to 800 days of social psychology isolation?
Man, we're going to find out. Yeah, it's a tough one. So there are several groups that have done experiments, nothing on the scale of 3 years, but we've studied small teams in isolation. There's a university out in Hawaii that mans a research station where they send crews of 4, 6, or 8 people on 1 month, 2 month, 6 month kind of missions. The Russians have done a year or longer isolation with crews, and there is certainly some psychology that goes on there. We don't know everything yet, for sure, but we've got a pretty good idea of what it will take to minimize the issues. And I think if we wanted to go ahead and do the mission, we'd have a reasonable start to be able to handle that kind of a challenge. Yeah, in the back.
So have you done some preliminary calculations to determine how many SLS launches you would need to send the return vehicle, the lander?
Sure.
Fuel for return and things like that?
Sure.
Have you done?
Yep.
How many metric tons all of that is and how many launches that is?
Absolutely. So the current thinking is we're building up an infrastructure around the moon, and it turns out the orbit that we're picking there is actually a pretty good one for staging things to go to other planets. So we're talking now about using the large SLS to throw things all the way out to the moon, which means we're limited to about 45-ish tons per launch. The landers won't go to that staging point because A, they're a little bigger than 45 tons, they can't get all the way to the moon, but B, they don't have to because they're going to go unmanned. They go ahead of the crew. And so you're basically looking at 1 to 2 launches per lander, depending on how skinny you can get it. 3 to 4 launches for the in-space propulsion to take the habitat out there, a launch for the hab and a launch for the logistics and a launch for the crew. Depending on how you can neck down the propulsion requirements, how much efficiency you can gain back in the propulsion, and how much printing we can do to not carry all of the spares in the world that we're going to need. We're looking at 8 to 10 to 12, depending on which approach you take. Yeah.
And we're talking about Block 2.
Yeah, the big one. The big one. And not only the big one, but the big one with the 10-meter fairing, because those landers need lots of surface area. And they need lots of deck space, because while these things are heavy that we're trying to land on Mars, they're also kind of voluminous. They take up a lot of space. You've got habitats that are, they need space. And so the 10-meter fairing on a Block 2 is really kind of where we're hoping to get. So, yeah.
Tom, for the habitat that you showed outside, what are you going to do about radiation shielding?
Well, I just lost the thing. Sorry.
There's a lot of different schemes. There's really two sources of radiation you have to worry about. There's the solar radiation, solar flares, and those sorts of things. And there's the galactic cosmic radiation. That's the heavy atoms that come from supernovas and stream across the universe. They're both bad. There's very little you can do to really shield yourself against galactic cosmic radiation. You just kind of have to live with the background noise. For solar flares and such, the current thinking is there's a minimal amount of radiation shielding you can put in the walls of the habitat with polyethylene, any kind of long chain carbon material will make a good radiation shield. Polyethylene is light. We like water is a great radiation shield, but it's kind of heavy. Polyethylene walls would help do some of that, and then a more robust storm shelter, where in the event of a solar flare, they'd be able to seek shelter inside a smaller volume. They wouldn't have to live in it for long. It's kind of like a tornado shelter here. You live in it when the thing's coming, and then most of the time you're not in it at all. What that does is it drastically cuts down on the mass that's required for the radiation shielding. Right? And we can predict the solar flares. We can see them before the particles get there, because the particles travel slower than the speed of light. And so there's ways to kind of know when that's about to happen. We were incredibly lucky that we didn't get a solar flare during Apollo. And we don't want to rely on luck for a 3-year mission. There's a good chance you're going to get something, right? But it's a storm shelter kind of mentality. Plus the supplies and the supply packaging gives us a fair amount of radiation protection too.
We're also looking at, once we retire a recycled product, the last print we do is a polyethylene tile.
Yeah.
And then you can just keep stacking those up once you've retired your plastic.
It's a great way to build up capability over time.
Can we presume that food production would be made from the surface of Mars?
Eventually, but not at the beginning. We don't know anything about growing food on Mars. Mark Watney grew potatoes, but it's going to be a while before that happens. So it's bringing everything we need with us, right? And that includes some amount of fresh food, which is a more challenging packaging situation, right? We'll have to do deep freezers and those sorts of things for some of that. Medication's another one that's kind of difficult to do shelf stable for 3 years. Nobody wants to eat MREs for 3 years in a small can. And so we're going to have to figure out a way to balance kind of the shelf stable stuff with the fresh stuff.
And that goes back to your psychology question.
Yeah.
Food is a huge part of psychology.
You want to find 4 people get really upset with each other in a small case, make them eat tuna out of a can for 9 months.
But I'll tell you, we are looking at taking stem cells and being
Yeah.
able to 3D print our meats. In all honesty, I mean, it has the real texture and the nutrition of meat. And then Ames Research Center is doing the synthetic biology for algae-based and plant-type growth. You can have little symbio factories.
Yeah, part of it's psychological. You want the same consistency, and things break down over time, and a lot of it is just nutritional, right? Food doesn't have the same nutrition 3 years from now that it had when it was packaged. And nutrition is going to be a pretty big deal for us. Yeah, that's a challenge.
So with multi-hundred days one way, would some food be grown on board en route?
Possibly, but we're not going to rely on it from the beginning. It's kind of like the lettuce we grew on Space Station a few years ago, right? We grew some lettuce. Well, how many boards did it take to let them eat it? It was a long time before they got food to eat the lettuce. So it's a slow process. Yeah.
First of all, this has been a fantastic presentation that the 4 of you have made. This is it strikes me as I listen to this that the technologies that each of you have been talking about seem reachable. I mean, we can get there, maybe longer, maybe shorter in each of these things. But the real question is the national and political commitment to go do. And so my question for you would be,
when are you four horsemen gonna take your show on the road? I mean, the Space Council is gonna be in town next week, and there's a strong element of preaching to the choir here, you know? And you need to preach to somebody other than the choir to help with getting this commitment. What's going on to make that happen?
Well,
Chinese are gonna land.
Anybody can answer.
Chinese are gonna land the man on the moon, and then we're gonna chase them. Yeah. So I can tell you that I preach as much outside of the choir as I possibly can, and I know that these three do too because I preach with them a lot. Part of it is the national will, part of it is the funding. The people who make the decisions, need some convincing, but some of them are on our side, and some of them are ready to stand up and do the things that need to be done to get the funding and to get the will. Everybody's program here is funded right now, not to the levels I think we'd like, right? And for now, but yeah, I think you guys can speak to it too.
For me, I think the message, not everybody may not want to sponsor space exploration, but to continue communicating clearly how much we get out of this on Earth. And like I said, my favorite part of the job is working with industry and academia. I work with more people outside of NASA than I do inside of NASA. This is our space program. It's our national space program. We're all part of it. And the benefits we get from it along the way of getting to these missions, that to me is the priceless part that really needs to continue to be communicated and championed.
And it needs to be something beyond tag and Velcro, you know?
Yeah.
There is a lot more, yeah.
Another reality of this is that we have other sustaining programs. We have a space station to pay for. That is part of the budget every year. We're building a launch vehicle. That's part of it. We're trying to plan some missions, but these things don't go away. So they call it the sand shark. You start stacking these things up, there's very little left for you to do any program planning for new missions. You're going to have to drop something off. So that's the nature of freeing up the funds. But what you've seen tonight as people that are in school, we're not rebels. We just see a future that I think can happen and can be better. And we ought to go. There are some people that have laid the foundation and they have established a very exciting start. And shame on us if we don't continue it.
Well, just what I want to add is, both Ben and Nick knows me pretty well. I've done them too. Is that part of the communication is not about budget, not about Congress. It's more about taking the risks. I hate to say this, but the phrase "no is not an option" is really, really bad. Because if we have to take a minor or big, okay, all those can break loose and you'll be on top of the block. So we don't have that luxury of this is the first step. And what we need is a landing on the first shot. That's fun. We can do another one. We can try again. Not that, lost lander. Okay, we're going to can't scrap it. Right. So that's one thing we need to communicate more is taking a risk. This is the baby step. And yes, after we go to Mars about 40, 50 times, yes, we can say we can do better.
I like to tell people that complain about how much we spend on the moon or on Mars that we've looked really, really hard and there are no cash registers on the moon. There are no cash registers on Mars. We spend that money here, right? Buzz Aldrin submitted a travel voucher for his trip to the moon. There wasn't a single expense after he left Kennedy, right? We spend the money here and we spend it in ways that return multiple times over. So, complaining that we spend money on space flight is a little rough to take. Yeah.
Do you get balanced bipartisan support from Congress in your views, each of you? Do you feel like it's balanced? Do you get support from both sides of the aisle?
Do I get to go to work tomorrow? Is that a fair question?
So, what about,
Alabama does pretty good because we have some senators that champion the cause. And, so a lot of it is politics. If the state can benefit or there are businesses in the state that can benefit, then, they're going to do it. But I don't know that there is opposition. It's just competing for the same dollar.
Yeah,
I will say this though, I will say we have got to stop separating, having these conversations about government, NASA versus commercial versus international. We do not have the luxury that other large organizations might have in funding. We have got to, the sooner we all team up and see that each one has strengths and weaknesses and we all have to be at the table to get there, the better. So we are all one team working toward these big goals, and it is a luxury to try to separate that. That we're
nice
not.
to hear your thoughts, thank you.
Well, that's what I wanted to ask is, where do we stand? I mean, what other countries are, laboring with us to try to get to Mars, to try to get back to the moon? And will China ever join with the countries, Russia, Japan, the EU, that we worked with on the space station?
So, international partnerships are not my, they're not my circus, right? But I can tell you that they're an ongoing discussion. We have international working groups that we're partnering on, that we chair in some cases. We do a lot of work with the Europeans. The Canadians just signed on to supply us a robotic arm for the Gateway of the Moon. There are a lot of international partnerships in play. China question is a whole different pathway.
The good news I'll say is there are certain times with policy that we may not all be on the same page internationally on the phasing of the priorities. I do feel like right now we're all on the same page across China, Russia, Europe, NASA, with moon, live on the moon, study the moon, and then go to Mars. I think that's, as far as I know, everyone's plan and we're phased. So I think that will help to enable those partnerships.
Also, I think we need to mature concepts of what it means to partner. Right now, if you look at the Gateway concept that NASA puts, there is a country associated with modules. An airplane is built with all kinds of different countries and companies, but it's one product. And I think we can parse these things out differently than giving somebody a module that's in the critical path and we scratch our head when they don't deliver it on time. My experience is things never have gone quicker when they're international, and they've never cost less. So you have to deal with that. The Chinese want their flag on the moon. So there is a certain nationalistic drive that really fuels what they're doing. And, ours is come play in our sandbox, and sometimes people are dragging their feet.
And I will say there's a big difference between the Apollo days. In the Apollo days, it was planting the flag. Now everyone's talking about staying there, and they're talking about resources and commercialization. That gets into a whole other category.
Well, we're past time, and I think in terms of everybody being able to go home and do the things that they're going to do, let's go ahead and have one final question, and go ahead and pick a person.
Oh, man, put that on me.
Yeah.
All right. Well, I see one hand
No
up, so that made it easy.
With the large Mars entry masses that you envision or would envision, would the sky crane be perhaps the desired terminal descent design?
So the sky crane is tough. The sky crane was what we used to land Curiosity, right? It put the propulsion system above the spacecraft, and as the spacecraft was coming through the atmosphere, it deployed along a long tether, and then the propulsion hovered some 20, 30, 40, 50 feet above it and kind of rested it down on its own legs, which solved the problem of deploying it, right? There can be an upper limit to how you can scale that up. And the challenge of slowing something down through the Martian atmosphere, the difference between the way a Curiosity landing happened and the way we're going to happen is we're so heavy, we have so much inertia coming through the atmosphere, that even when the aerodynamics stop working for us, we're still traveling supersonically. And supersonic retropropulsion is something that we've not done on Mars before. And it is a big challenge, and it's something that SpaceX actually helped us figure out because they've been doing it with returning their cores. But it's something that for the size of the payload you're talking about, 8 20,000 pound engines all operating supersonically. makes, you know, the kind of guidance and control that you need to be able to do something like a sky crane really, really challenging. And the hoist and winch system for something that's 20 times bigger than the rollers is a big deal too. So, yeah, I think it's a challenge. The other challenge is the way we're landing, we got to figure out a way to get everything off the deck, and the deck is 10 feet off the ground. So, yeah, it's one thing or another. Right? We're not gonna find a silver bullet. Yeah.
Well, in closing, I was just thinking that there are few places in the world, let alone the United States, where you could get the kind of presentation you got this evening. And these are all local people. And you got a glimpse of the future, but it's a realistic future, and it can happen. So thank you for your time coming here, and I thank my fellow panelists.
3, 2, 1, 0.